In 1998, astronomers were tracking distant exploding stars, expecting the universe to follow a familiar pattern. Gravity pulls things back together. Over enough time, the expansion of the universe should gradually lose momentum. The measurements began arriving. At first, the numbers looked like routine observations. Then the pattern refused to cooperate. The distant supernovae appeared farther away than expected. The light reaching Earth carried the same unsettling message again and again. The expansion was not slowing down. It was speeding up. That single result did more than challenge a theory. It broke the future astronomers thought they understood. Predictions that once seemed straightforward suddenly became uncertain. The universe was moving toward a different future than anyone had predicted. The problem was not a small correction. The trend pointed in the opposite direction. Astronomers could still see galaxies moving away. They could still measure the expansion. But the future was no longer behaving the way their observations said it should. Something was affecting the fate of the universe in a way nobody had anticipated. And if expansion was accelerating, a more troubling question immediately followed. What happens to the parts of the universe that are already moving away? As astronomers followed the implications of the discovery, the problem stopped looking like a surprising result and started looking like a loss. Galaxies were already moving away from one another. That much was expected. But if expansion continued accelerating, then more and more of those galaxies would keep pulling farther apart at an increasing rate. At first, nothing dramatic appeared in the sky. Telescopes still point outward. Light still arrives. Maps of the universe still fill with distant objects. Then the consequence begins to emerge. Every distant galaxy is constantly sending something toward us. New light, new events, new information about what is happening across space. But as expansion accelerates, growing regions of the universe drift toward a state where future observations become harder to obtain. The loss is subtle because it happens gradually. A galaxy visible today may remain visible for an extremely long time while quietly providing less and less new information. Yet the flow of new information from distant regions becomes increasingly restricted. The observable universe is not simply expanding. Parts of it are slowly becoming harder to learn from. That changes the meaning of the discovery. The sky is no longer a permanent archive waiting to be examined whenever technology improves. It becomes a landscape where observable territory can be lost. And once information stops arriving from a distant region, an uncomfortable possibility follows. Can any future technology recover what has already disappeared? A natural response is to assume the problem will eventually be solved, the same way countless other observational limits have been solved. Build a better instrument. That approach has worked before. Again and again, astronomers pointed new telescopes at regions that seemed exhausted of discovery and watched them fill with detail. Areas that looked sparse revealed hidden galaxies. Signals once considered too faint became measurable. Distance after distance stopped being a barrier. The pattern became familiar. Every major upgrade pushed the visible frontier farther out. From Hubble to Webb, the map kept growing. That history creates a powerful expectation. If part of the universe becomes difficult to observe, future technology should close the gap. If information appears lost, a larger telescope or a more sensitive detector should eventually recover it. The solution seems obvious because it has worked every time before. The sky may be changing, but the tools are changing too. And as long as technology keeps advancing, there seems to be little reason to believe any missing region of the universe will stay missing forever. At least, that is what the historical record appears to suggest. The assumption fails when astronomers follow the problem far enough. A larger telescope can collect faint light. A more sensitive detector can recover weak signals. Better engineering can extend observation far beyond previous limits. But all of those solutions depend on the same requirement. The light has to arrive. As expansion continues, distant galaxies keep moving farther away. Eventually, some reach a point where any new light they send will never reach the observer. The galaxies still exist. They continue producing light. Events continue unfolding inside them. But the new information never arrives. Imagine pointing a future telescope at the exact location. The mirror grows larger. The instruments become more precise. The observation runs longer. Nothing changes. There is no hidden signal buried in noise, no missing technology waiting to be invented, no upgrade capable of reaching farther into that region. The evidence is absent because it never reaches the telescope in the first place. That is where the historical pattern breaks. Every previous observational limit assumed the information was still out there, waiting to be collected. This limit is different. The information still exists. It just never arrives. The loss is no longer a problem engineers can solve. It is built into the way the universe behaves. A civilization can build better instruments forever and still fail to recover what has disappeared beyond that boundary. The obstacle is not the telescope. The obstacle is reality itself. And if enough distant regions stop sending observable information, the appearance of the universe begins to change in a much deeper way. What remains visible after enough evidence is gone far in the future. Observers may look into the sky and see something very different from what we see today. The larger cosmic landscape continues disappearing beyond reach until only their local gravitationally bound group remains visible. The surrounding universe does not collapse. It does not stop existing. It simply stops providing new, observable evidence. Telescopes still operate. Measurements still improve. Science still advances. But the raw material available for discovery becomes smaller. Those future astronomers could possess instruments far beyond anything humanity has ever built, and still have access to less evidence than we do. They could measure their remaining universe with extraordinary precision. Yet when they look outward, most of the evidence that revealed the true structure of the cosmos to us would already be gone. The consequence is difficult to ignore. They may know more science than we do, while having less evidence than we do. Not because it failed to develop better technology. Not because it made a mistake. But because the observable record itself changed. The universe we see today is not simply a larger version of theirs. It contains evidence that will not remain available forever. Knowledge of the cosmos depends on access to evidence. And that evidence is not guaranteed to remain available forever. The discovery in 1998 was not just that the universe is accelerating. It was that humanity may be living during a temporary moment when the universe still reveals enough of itself to be understood.